In this video, we're going to be concerned about rotational motion, how fast an object is moving around a circle. So let's start with the circle. The distance between the center of the circle and any point on a circle is the radius. The angle theta is the angle between these 2 points. And the distance at the edge of the circle between those 2 points is known as the arc length. The arc length can be calculated by multiplying the angle in radians times the radius. So let's say if you have an angle of 1 radian, and let's say the radius is 5 meters. The arc length is 5 meters per radian, and so 1 radian will give you an arc length that's 5 meters. So a radian is defined as the angle subtended by an arc whose length is equal to the radius. Now let's say if the angle was 2 pi radians. So that would represent the entire circle. 2 pi radians is equal to 360 degrees. Notice that you get the equation for circumference. Circumference is the arc length of the entire circle. So that's where this equation comes from. Now make sure you know how to convert between degrees and radians. So here's an example. Let's say if we want to convert from 90 degrees to an angle in radians. What we need to do is multiply by 2 pi over 360, or simply pi divided by 180. Pi radians is 180 degrees, and 2 pi radians, that's a full circle, that's 360 degrees. So notice that the symbol degrees cancel. So 90 over 180. If you cancel the 0, that's 9 over 18. So this is the same as pi over 2. So that's how you can convert from degrees to radians. Now, if you wish to convert from radians to degrees, multiply by 180 over pi. For example, let's say if the angle is pi over 4 in radians. Multiply by 180 degrees divided by pi. So pi will cancel, and it's simply 180 over 4, which is about 45 degrees. Now, there are some other equations that we need to go over. For example, velocity is defined as displacement divided by time. Angular velocity, or omega, is angular displacement divided by time. Displacement usually has the units meters, and time is in seconds, so velocity is meters per second. Angular displacement is usually measured in radians, and the time is in seconds, so the angular velocity will have the unit radians per second. Notice the similarities. Now, acceleration is the rate of change of velocity, or is the change in velocity divided by the change in time. Angular acceleration is very similar. It's the rate of change, or it's the change of angular velocity with respect to time. So you could say it's W over T. And really, omega is basically the change, or the angular displacement, the change in theta over the change in t. You could describe it that way as well. Now this equation gives you the average angular velocity. If you want to find the instantaneous angular velocity, it's the limit as delta t approaches 0. So as delta t becomes very, very small, then this quantity approaches the instantaneous angular velocity, whereas this equation is the average angular velocity. The same is true for angular acceleration. The average angular acceleration is the change in the angular velocity divided by the change in time, whereas the instantaneous angular acceleration is the limit as delta t approaches 0 for the equation change in angular velocity over change in time. So this is the instantaneous angular acceleration. Now going back to the circle. So we said that the arc length is equal to theta. It's equal to the angle in radians, theta times r. So really, the arc length s is basically the distance traveled in linear motion. If a wheel is rotating, if the arc length is, let's say, 5 meters, as it moves, it's going to travel a horizontal distance of 5 meters. So s can be the same as just linear distance, so to speak. So we could say that linear displacement or distance, if it's traveling in the same direction, displacement and distance is the same whenever you're moving in the same direction. Unless direction changes, then distance and displacement can be different. So the linear distance or displacement is equal to theta times the radius. Now, if we divide both sides by time, notice the equation that we're going to get. Displacement over time is velocity, and angular displacement divided by time is the angular velocity. So we're going to get this equation. Make sure you're aware of this equation because it's very useful. Now the change in velocity is equal to the change in the angular velocity times the radius. If we divide this equation by time, we can get another equation. The change in velocity divided by time is acceleration, particularly tangential acceleration. And the change in angular velocity divided by time is the angular acceleration, represented by the symbol alpha, times the radius. So make sure you know this equation and this one too. So notice the similarities. Linear displacement is equal to angular displacement times the radius. Tangential velocity is equal to the angular velocity times the radius. And tangential acceleration is equal to the angular acceleration times the radius. Now what exactly do we mean by tangential velocity and tangential acceleration? So let's say if you have a wheel that is moving in, let's say, in a counterclockwise direction. Let's say we have a point on the circle. So this point has a tangential velocity that is directed in this direction. And that tangential velocity is equal to the angular velocity, that's how fast the wheel is spinning, times the radius. Now what about acceleration? Whenever an object changes direction, there's always a centripetal acceleration. also known as a radial acceleration. Now, at this point, the object has a tangential acceleration, which is tangent to the circle. It's in the same direction as the tangential velocity. It also has a radial acceleration, or a centripetal acceleration, that always points towards the center of the circle. And that keeps this point always directed, or always turning in the path of the circle. So therefore, this object has a net acceleration vector that points in this direction. That acceleration vector is equal to the square root of the radial acceleration and the tangential acceleration. So if we draw a picture, here's the radial acceleration. It's pointing towards the center of the circle. Here's the tangential acceleration. And the net acceleration is the hypotenuse of the triangle. So according to the Pythagorean theorem, a squared plus b squared is equal to c squared. So therefore, the square of the tangential acceleration plus the square of the radial acceleration is equal to the square of the net acceleration of a point on a circle. So if you take the square root of both sides, you will get this equation. So make sure you're aware of the terms the tangential acceleration, radial acceleration, and net acceleration. So remember, radial acceleration or centripetal acceleration is equal to the square of the velocity, that is the tangential velocity, divided by the radius. And the tangential acceleration is equal to the angular acceleration times the radius. So make sure you're aware of these two equations. And don't forget, velocity is equal to the angular velocity times the radius. So the centripetal or the radial acceleration, which is v squared over r, you can also write it this way. So v is w times r. And once you square it, you get this equation, w squared r squared over r. You can cancel one of the r's. So the radial or the centripetal acceleration is the square of the angular velocity times the radius. So if you know the angular velocity, you can find the centripetal acceleration. Or if you know the tangential velocity, you can find it as well. Now let's review some of the units in this equation. So we say that the linear displacement is equal to the angular displacement times the radius. The angular displacement is measured in radians, and the linear displacement is measured in meters, provided if the radius is in meters. But you can think of the radius as being as meters per radian, so that the unit radians cancel. Now for this one, we know that velocity is equal to angular velocity times the radius. The omega symbol, or the angular velocity, has the units radians per second. Now it could be radians per minute or radians per hour, but the most common unit is radians per second. So velocity is going to be meters per second, assuming if radians has unit meters in it. Now the next equation is linear or tangential acceleration is equal to angular acceleration times the radius. We know that linear acceleration has units meters per second squared. Angular acceleration is radians per second squared. Now some other equations that you need to be familiar with are frequency and period. Frequency represents the number of cycles per second. So it's the number of cycles divided by the time. Now the cycles could be the number of revolutions. For example, let's say if a wheel makes 10 revolutions in 2 seconds, or 10 cycles in 2 seconds. So the frequency would be 5 revolutions per second. The period is the reciprocal of the frequency. It's the time it takes to complete 1 second. So it's the time divided by the it's the time divided by the number of revolutions. So in this case, the time is 2 seconds, and during that time 10 revolutions occur. So the period would be 1/5. Typically the period is just measured in seconds, but it's really seconds per revolution. It's the time it takes to make 1 revolution around a circle. But in a physics problem, you'll see that period just has the unit seconds though. Frequency is 1 divided by the period, and the period is 1/frequency. The unit for frequency is the hertz, or hertz, which is really 1 revolution per second. And the unit for period, as we mentioned, is seconds per revolution. Omega, or angular velocity, is equal to 2 pi f. That's how you can relate angular velocity to frequency. So if you know the frequency, then you could easily find the angular velocity. Now let's look at the units. So let's perform dimensional analysis on this equation. We know that pi is really measured in radians, and 1 revolution around a circle is 360 degrees, which is 2 pi radians. So 2 pi radians is equal to 1 revolution. And frequency is measured in revolutions per second. So notice that the unit revolutions cancel, and thus you get the units for omega, which is in radians per second. As you can see it here, these are the units that do not cancel. And so this is another equation that you want to know. Now it turns out that there are some other equations that you need to know, but let's make a comparison between the linear equations and the angular equations. So we know that linear displacement is equal to velocity multiplied by time, and angular displacement, which we'll call theta, is equal to angular velocity multiplied by time. So this is at constant speed. If there's no acceleration, if there's no linear acceleration or angular acceleration. If v and w are constant, then those two equations apply. Now, if they're not constant, then let's say if we have constant acceleration, linear displacement is equal to 1/2 the initial speed plus the final speed multiplied by time. Likewise, angular displacement is going to be 1/2 times the initial angular velocity plus the final angular velocity multiplied by time. Final velocity is equal to initial velocity plus at. Final angular velocity is equal to initial angular velocity plus angular acceleration multiplied by time. Look at the similarities between the two equations. Final velocity squared is equal to the initial velocity squared plus 2 times the linear acceleration times the displacement. Final angular velocity squared is equal to initial angular velocity squared plus 2 times the angular acceleration times the angular displacement. And there's one more equation you need to know, and it's this one. Displacement is equal to the initial velocity multiplied by the time plus 1/2 times the acceleration multiplied by t squared. So angular displacement is equal to the angular velocity, the initial angular velocity multiplied by the time plus 1/2 angular acceleration times t squared. So now you have the linear kinematic equations and the rotational kinematic equations. So if you know the linear kinematic equations, simply replace displacement with angular displacement. If you see a d, put a theta there. You can replace linear or tangential velocity with angular velocity, and tangential acceleration with angular acceleration. Now let's work on some problems. A disk spins at a constant rate of 20 revolutions in 4 seconds. What is the period and frequency of the disk? So let's start with that. So the frequency is the number of cycles per unit time. So the disk makes 20 cycles or 20 revolutions in a time period of 4 seconds. So the frequency is 20 divided by 4, or it's 5 revolutions per second, which equates to 5 Hertz, which is also a unit of frequency. Now the period is the time divided by the number of cycles, or it's simply 1 divided by the frequency, which is 1 over 5. So the period is 0.2 seconds, or specifically 0.2 seconds per revolution. So it takes 0.2 seconds for the disk to make 1 revolution. But in 4 seconds, it makes 20 revolutions, which means that in 1 second, it makes 5 revolutions. Now that we have the frequency, how can we calculate the angular speed in radians per second? So omega is equal to 2 pi f. So it's 2 pi radians per revolution multiplied by 5 revolutions per second. So it's 10 pi radians. And pi is about 3.14. So 10 times 3.14 is about 31.4 radians per second. So that's the angular speed. Now, what is the tangential velocity of a point 50 centimeters from the center of the disk? So let's say here's the center, and the point is somewhere at that location. So 50 centimeters is basically 0.5 meters. A 100 centimeters is equal to 1 meter. So 50 centimeters is half of a meter. If you want to see the conversion, this is what you need to do. Start with 50 centimeters. There's 100 centimeters per meter. You need to know that. And you want to set it up in such a way that the unit centimeters cancel. So 50 divided by 100 is 0.5 meters. So that's the radius, the distance between that point and the center of the circle. So our goal is to find the tangential velocity. Tangential velocity is the angular velocity times the radius. So it's going to be 31.4 radians per second times the radius, which is 0.5 meters, per radian. So the unit radians cancel, and we're going to get the unit meters per second. So it's half of 31.4, which is about 15.7 meters per second. Now, how can we calculate the net acceleration? Now, we need to realize that there's two types of acceleration in this problem. The net acceleration is the square root of the radial acceleration, or the square of the radial acceleration, and the square of the tangential acceleration. Now, the first thing that we want to know is that the disk spins at a constant rate. So if it's spinning at constant speed, that means that the tangential acceleration is 0, because the tangential velocity is constant. So if the disk is not speeding up, the tangential acceleration is 0. However, because the point is changing direction, we do have a centripetal or radial acceleration. There's two ways in which you can have an acceleration: if the object speeds up, or if it changes direction. If it speeds up, then the tangential acceleration is not 0. But since it's moving at constant speed, the tangential acceleration is 0. Now this point is spinning, it's changing direction as it moves around a circle. Anytime an object changes direction, it has a radial acceleration. And the radial acceleration is equal to v squared over r, or we can use this equation, omega squared times r. Let's use that equation to calculate it. So it's going to be w, which is 31.4 squared, times the radius of 0.5 meters. And so this is going to be 492.98. Now, the net acceleration for this particular problem is the same as the radial acceleration, since the tangential acceleration is 0. For example, if we plug it into the formula, it's going to be the square root of 492.98 squared plus 0 squared. The square root of 492.98 squared is simply 492.98. And the units for acceleration is typically meters per second squared. And so that's it for that problem. The wheel of a car spins at 30 revolutions per minute for 5 minutes. The diameter of the wheel is 1 meter. What is the angular speed of the wheel in radians per second? So right now we have the angular speed in revolutions per minute, which you can think of as the frequency, which is usually revolutions per second. But we can simply convert it to get the angular speed in radians per second. So 30 revolutions per minute. And we know that there's 2 pi radians in 1 revolution. 1 revolution is a full circle, which is 360 degrees, and that's equal to 2 pi radians. So the unit revolutions cancel. And now let's convert minutes to second. 1 minute is equal to 60 seconds. So now we have the units that we want, which is radians per second. So it's 30 times 2 pi divided by 60. Well, 30 times 2 is 60, so we can cancel the 30, the 2, and the 60. So it's simply pi radians, which is about 3.14 radians per second. Let's not forget the unit seconds on the bottom. So this is the angular speed. Now that we have the angular speed in radians per second, what is the angular displacement of the wheel during this time period. The angular displacement is equal to W multiplied by T, or omega times T. So since omega has unit seconds, we want time to be in seconds as well. So let's convert 5 minutes into seconds. There's 60 seconds in a minute, so 5 times 60 is 300. So T is 300 seconds. So now we can calculate the angular displacement. So it's 3.14 radians per second times 300 seconds. And so we could see that the unit seconds will cancel, which will give us the angular displacement in radians. So it's 3.14 times 300. And so that is equal to 942 radians. Now, how far does the car travel in 5 minutes? There's many different ways in which we can do this. We're going to talk about 2 ways to get the answer, so that you're familiar with the equations and how to use them. But right now, let's write out the information that we have. So we said that omega is equal to 3.14 radians per second. And the angular displacement is 942 radians. And T is 300 seconds. So once you have the angular displacement, you can use that to calculate the distance using this equation. So D is equal to theta times r. So the linear displacement, D, is equal to the angular displacement, which is 942 radians, times the radius, which is it's not 1 meter. The diameter is 1 meter, so the radius is half of a meter, or 0.5 meters per radian. So if we multiply 0.5 meters per radian, these units will cancel. So even though the radius is 0.5 meters, I want you to understand that 1 radian would equal an arc length of 0.5 meters. So that's why I usually write it as 0.5 meters per radian, so you can see how the units work out in this problem. So what is half of 942? Half of 942 is 471. So the car travels 471 meters in this time period of 5 minutes. So that's one way to get the answer. Now let's see if we could find another way to get the same answer. The other way is to find the tangential velocity. The tangential velocity is equal to the angular velocity times the radius. And the angular velocity is 3.14 radians per second. And the radius is 0.5 meters per radian. So the unit radians cancel, and it's going to be meters per second. So 3.14 times 0.5, and that's about 1.57 meters per second. So now that we have the tangential velocity, we could find the distance using this equation. D is equal to VT. So 1.57 meters per second multiplied by the time of 300 seconds will give us the linear displacement, which is 471 meters. So both ways you can get the same answer. So if you have the tangential velocity in meters per second, make sure the time is in seconds and not minutes. So pay attention to the units for these problems. A centrifuge accelerates uniformly from rest to 3,500 revolutions per minute in 500 seconds. What is the angular acceleration? So let's find it in radians per second squared. So first, let's convert revolutions per minute to radians per second. So we know the initial angular speed is 0. Let's find the final angular speed. And the time is 500 seconds. So 3,500 revolutions per minute, and in 1 minute there's 60 seconds, and there's 2 pi radians per revolution. So the unit minutes cancel and revolutions cancel. So now we have the angular speed in radians per second. So it's 3,500 times 2 pi divided by 60. So the final angular speed is 366.5 radians per second. So what equation do we need in order to calculate the angular acceleration now that we have the final angular speed? The equation that we need is this one. Omega final is equal to omega initial plus alpha t. So the final angular speed is 366.5. The initial is 0. We're looking for alpha, and the time period is 500 seconds. So it's simply 366.5 divided by 500. So the angular acceleration is 0.733 radians per second squared. Now, how can we calculate the net acceleration now that we have the angular acceleration? What do we need to do? In order to find the net acceleration, we need to find the radial acceleration and the tangential acceleration. So let's start with the tangential acceleration. Now we're going to find the net acceleration once it reaches a final speed of 3,500 RPMs. The tangential acceleration is alpha times r. So alpha is 0.733, and the radius, the distance between the test tube and the center of rotation, that's 15 centimeters. If you divide that by 100 to convert it to meters, that's 0.15 meters. So it's 0.733 times 0.15. So the tangential acceleration is about 0.11 meters per second squared. Now what about the radial acceleration? Let's use this equation to calculate it. W squared times r. So let's calculate the radial acceleration at the final angular speed of 366.5. So it's going to be 366.5 squared times 0.15. And this is 20,148, which is pretty high since the angular speed is very high as well. Now the net acceleration, which is the square root of the square of the tangential acceleration and the square of the radial acceleration. Because the radial acceleration is so much larger than the tangential acceleration, the net acceleration is going to be the same as 20,148 as the radial acceleration. If you plug it into the formula, this is going to be about 20,148. Now what about part B, which I pretty much skipped? How can we calculate how many revolutions the wheel makes during this time period? What can we do to get the answer? Now there's many equations that you can use. Let's use about maybe 2 equations. One equation that we can use is this one. The angular displacement is equal to the initial angular speed multiplied by the time plus 1/2 alpha t squared. So the initial angular speed is 0. The angular acceleration is 0.733, and the time is 500 squared. So the angular displacement is 91,625 radians. Now we want to know the revolutions that it made during this time period. So we need to convert radians to revolution. Now 1 revolution is equal to 2 pi radians. So we simply need to divide it by 2 pi. So the wheel, or the centrifuge, I should say, it makes 14,500, and we can round it to 83 revolutions in this time period. So that's one way you can get the answer. Now there's another equation that you can use too to get that same answer. If you don't know the angular acceleration, and if you know the initial and final angular speed, you can use this equation. The angular displacement is 1/2 the initial plus the final angular speed multiplied by the time. So basically, if you add the initial and final angular speed and divide by 2, what you get is the average angular speed. So it's the average angular speed multiplied by the time. So it's 1/2 of 0 plus 366.5 multiplied by the time of 500 seconds. So half of 366.5, that's 183.25 times 500, and you get the same number, 91,625 radians, and then convert it to revolutions as we did in the last example. So that is it for this problem. That's how you could find the number of revolutions that the centrifuge made in that time period. Let's try this problem. A disk accelerates from rest at a rate of 5 radians per second squared. So that is the angular acceleration. What is the angular speed after it makes 800 revolutions? So we know the initial angular speed. It's 0 since it starts from rest. We're looking for the final angular speed, and we know that the angular displacement is 800 revolutions. So let's convert revolutions into radians. Now we know that 1 revolution is equal to 2 pi radians, and so the unit revolutions cancel. Therefore, the angular displacement is 1600 pi radians. Now, what equation do we need that contains omega final, omega initial, alpha, and theta? The equation that we need is W final squared is equal to the omega initial squared plus 2 alpha times theta. W initial is 0, alpha is 5, and theta is 1600 pi. So 2 times 5 is 10, and 10 times 1600, that's 16,000 pi. So now to find the final angular speed, we need to take the square root of both sides. And so the final angular speed is 224.2 radians per second. Now that we have the final angular speed, what can we do to calculate the time it took to reach that angular speed? What equation should we use? The best equation to use at this point is this one. So now that we have the final angular speed, which is 224.2, and we have alpha, we can now find the time. So it's simply 224.2 divided by 5. And so it took 44.84 seconds to reach that final angular speed. A bike slows down from 12 meters per second to rest over a distance of 200 meters. The diameter of the wheels are 80 centimeters. What is the initial and final angular speed in radians per second? So let's begin. We know that v is equal to omega times r. Now, the final speed we know it's 0. So the final angular speed must also be 0. The initial speed is 12 meters per second. So let's solve for the initial angular speed. Now, if the diameter of the wheels is 80, that means that the radius has to be 40 centimeters, which is 0.4 meters. So 12 divided by 0.4 is 30. So the angular speed is 30 radians per second. So that is the initial angular speed. The final is 0. Now what about the angular displacement? How can we calculate the angular displacement? Now we already have the linear displacement, which is 200 meters. So we can use this equation. Linear displacement is equal to the angular displacement times the radius. So d is 200 meters, and the radius, as we mentioned before, is 0.4 meters. So 200 divided by 0.4 is 500. So the angular displacement is 500 radians. So now that we have the angular displacement, how can we calculate the average angular acceleration? So what equation has the initial and final angular speed, alpha and theta? So we need to use this equation. Omega final equals omega initial squared plus 2 times alpha times theta. So the final speed is 0. Initial is 30. And the angular displacement is 500. 30 squared is 900. 3 times 3 is 9. You just add the extra 0. And 2 times 500 is 1,000. So we need to subtract both sides by 900. So negative 900 divided by 1,000 will give us an angular acceleration of negative 0.9 radians per second squared. Now the reason why it's negative is because the bike is decelerating, it's slowing down. So the angular acceleration has to be negative because the angular speed is decreasing. So let's put this information here. Now the next thing that we need to do is we need to find the time it takes for the bike to come to a complete stop. So the equation that we can use to find the time is this one. There's plenty of other equations that you can use, but personally I think this is the easiest. The final angular speed is 0, initial is 30, alpha is negative 0.9, so let's solve for t. So if we move the 30 to the other side, it's going to be negative 30 and then divided by negative 0.9. So it's going to take 33.33 seconds for the bike to come to a complete stop. Now we can confirm this answer using linear kinematics. We have the initial, the final speed, and we have the distance. So we could find the time. The initial speed is 12 meters per second, final is 0, and the displacement is 200. So we can use this equation. D is equal to 1/2 V initial plus V final times t. So the displacement is 200. Initial speed is 12, final is 0. Let's solve for t. Half of 12 is 6. And so it's going to be 200 divided by 6, which will give us the same answer of 33.3 seconds. Now the next thing that we're going to talk about is torque. Torque is the rotational equivalent of force. Let's say if this is the top view of a door, and this is the hinge of the door, the axis of rotation. If you apply a force, the door is going to turn in this direction, in the counterclockwise direction. Because this force is causing the door to rotate, it's creating a torque. The torque is the product of the force and the lever arm, or the moment arm. In this case, the lever arm is the distance between the line of action and the axis of rotation. So let's say if you apply a force of 100 newtons at a distance of 2 meters from the axis of rotation, then the torque applied is 100 times 2, which is 200 newtons times meters. Now, is it easier to push a door at the edge, in the middle, or by the hinge near the axis of rotation? What would you say? It turns out that it's easier to apply a force at the edge of the door. It doesn't require much effort. But if you apply a force at the middle of the door, it's going to take more effort to rotate, or to cause the door to rotate. If you cut the distance in half, to have the same amount of torque, you need to double the force. So you need to apply a force of 200 newtons at a distance of 1 meter from the axis of rotation to produce the same torque of 200 newtons times meters. Now let's say if you apply the force at a distance 0.5 meters from the axis of rotation, it's going to be very hard to push the door. It's going to require a force of 400 newtons to produce the same torque to cause the door to rotate. So as you can see, it's very easy to push the door at the edge because the lever arm is greater, and so the torque is greater. But it's very difficult to push the door by the hinge because the lever arm is so much smaller, and so to get the same amount of torque, you have to exert a greater force to push the door at that location. So that is torque. It's the product of the force and the lever arm. And by the way, in some textbooks, you might see the torque as being not just F times L, but also F times R. So sometimes R could be used as the moment arm or the lever arm. Now let's try another problem. So let's say if we have another door, and instead of applying a force that's perpendicular to the door, what if we apply a force that's parallel to the door? If you apply a force that's parallel to the length of the door, in this case, there is no torque. The torque is going to be zero. It's not going to rotate. Conceptually, you know it's just not going to move, so there's no torque. In order to create a torque, you have to apply a perpendicular force. Now, what if we apply a force at an angle? Let's say if we apply it here, a force of 100 newtons. And let's say at the point of contact, the distance between the axis of rotation and the point of contact is, let's say, 5 meters. How can we calculate the force? And let's say that this angle, theta, is equal to 30 degrees. So if you have the angle between the force and the length of the door in this case, the torque is equal to the force times the moment arm times sine theta. The moment arm is really just r sine theta, by the way. I'll explain why. R is simply 5. So it's going to be 100 times 5 times sine 30. Sine 30 is a half. Half of 500 is 250. So the torque is positive 250. I'm going to need a new picture. So if we apply a force at this point, what I'm going to do is I'm going to extend the force. This line that I drew, this is known as the line of action. That's where the force is being applied. The moment arm is perpendicular to the line of action. So this is the moment arm. And r is the distance between where you apply the force and the axis of rotation. So in this case, we said r is 5. Now the angle between the force and the door is the same as this angle here. In geometry, you know that these two angles are equal. They're vertical angles. So let's say, for example, if this is 40, this angle has to be 140 because this forms a linear pair. They have to add up to 180, which means this is 40 because these two form a linear pair. So therefore, these two angles are congruent. So what equation can we use to relate r and the moment arm? Now first, we need to realize that the torque is the product of the force and the moment arm. The moment arm is this value, is the perpendicular component of r, the part that's perpendicular to the line of action, and it's between the line of action and the axis of rotation. So that's this distance right there. Now, according to SOHCAHTOA, if we go back to trig, sine is opposite over hypotenuse. So sine theta is equal to the opposite side of that triangle, which is the moment arm, divided by the hypotenuse. Since this is the 90-degree angle, across from it is the hypotenuse, which is r. So sine theta is the moment arm divided by r. So if we multiply both sides by r, we can see that the perpendicular component, or the moment arm, is just r sine theta. So the torque is equal to force times r times sine theta. That's one way you can calculate the torque. Another way in which you can get the same answer, And sometimes it might be easier to think about it this way. Let's say if you apply a force at this point, it's equivalent to applying a force at this point as well. This force has a vertical component and a horizontal component, f of x. Now, f of x, the horizontal component, doesn't create a torque because it's parallel to the door. The vertical component, Fy, is what creates the torque. So if you take Fy and you apply it at the same point as you apply F, then the torque created is simply R times Fy. You're going to get the same answer if you do it this way. Now, let's see why that's the case. So this is f of x, this is Fy, and this is F. Now keep in mind, theta is the angle between F and R. So theta is here. Sine theta is equal to the opposite side. Opposite to theta is Fy, divided by the hypotenuse, which is simply F. That's across the 90-degree angle. So multiplying both sides by F, we can see that Fy is F sine theta. So the torque is equal to the perpendicular component of the force, Fy, the part that's perpendicular to R, multiplied by R, and Fy is F sine theta. So you get the same equation, Fr sine theta. So make sure you remember this. If you apply force, F, and if you know the angle between R, let's say R is this distance here, but if you draw a line and extend it, so if you know the angle between F and R, and if you have R, the torque is simply Fr sine theta, if it's at an angle. So try this problem. Let's say if we apply a force of 200 newtons, and it's at an angle of 60 degrees relative to the door in this case. And the distance between the axis of rotation and the point in which you apply the force, let's say it's 10 meters. So the torque is going to be F sine theta times R. So it's 200 times sine of 60 times 10. So 200 times 10, that's 2,000. And sine 60 is root 3 divided by 2. So 2,000 divided by 2 is 1,000. So it's 1,000 root 3. And the square root of 3 is about 1.73. So this is about 1730, roughly, newtons times meters. Now, is the torque positive or is it negative? What would you say? Whenever a force causes the object to rotate clockwise, the torque is negative. If the force causes the object to rotate into the counterclockwise direction, that's opposite to the motion of a clock, the torque is positive. If you think of trig, for those of you who have taken that class, where is the angle measure of, let's say, positive 60 degrees? Positive 60 degrees is in quadrant 1. You would have to move this way. Now let's say if you want to find the measure of negative 80 degrees. Negative 80 degrees is over here. You would have to travel in the clockwise direction. So the same is true for torque. So if you travel clockwise, the torque is going to be negative. And if you travel in the counterclockwise direction, the torque will be positive. Now let's say if we have an object, and let's say this is the axis of rotation. It can rotate this way, it can rotate that way, or this way. Let's say it's free to rotate about the center. If we apply a force of 200 newtons at a distance of, let's say, 3 meters, and if we apply another force of 100 at a distance of 4 meters, and another force of 300 at a distance of, let's say this is 2.5 meters. What is the net torque on a system? And will this object rotate in, let's say, the clockwise direction? Or will it rotate, this is the counterclockwise direction, or will it rotate in the clockwise direction? What would you say? So we need to calculate the net torque. Let's call this F1, F2, and F3. So we need to find the sum of all the torques acting on the system. So that's T1 plus T2 plus T3. So T1, we know it's positive. F1 will cause the object to rotate in the counterclockwise direction, so it's going to create a positive torque. So T1 is simply 200 times 3. So that's positive 600 newtons times meters. Now T2 will cause the object to rotate in the counterclockwise direction, so it's going to create a positive torque. So T2 is 100 times the moment arm, or the lever arm, of 4. So it's positive 400. Now what about T3? So this force will cause the system to rotate this way in a clockwise direction. So it's going to create a negative torque. So T3, let's write it here. That's going to be the force times the moment arm of 2.5. 300 times 2 is 600, and 300 times 0.5, or half of 300, is 150. So 600 and 150 will create a torque of 750, but it's negative. So to find the sum of all the torques, we need to add everything. So torque 1 is positive 600. Torque 2 is positive 400. And torque 3 is negative 750. 600 plus 400 is 1,000 minus 750, that's 250. So the net torque of the whole system is positive 250. So this object is going to rotate in the counterclockwise direction. Now what if we have a compound wheel? So we have two circles, and let's say if we apply a force of 300 newtons and another force of 400 newtons, and let's say that the radius of the larger wheel, let's say it's 2 meters, and the radius of the smaller wheel is 1 meter. What is the net torque acting on this system? So let's call this F1 and F2. So torque 1, is it clockwise or counterclockwise? F1 is going to create a torque that is rotating in the clockwise direction. So it's going to create a positive torque. And that torque is simply 300 times 2, which is 600. F2 will create a torque that's going to cause the wheel to rotate in this direction. That's the counterclockwise direction. By the way, T1 is clockwise, so I need to put the negative sign. But torque 2 is counterclockwise, so this is going to create a positive torque. And that's going to be 400 times the moment arm of 1, which is the radius of the smaller circle. So this is going to be positive 400. So the net torque of the whole system is T1 plus T2. So it's negative 600 plus 400. So it's negative 200. So the net torque is going to cause the system, or the wheel, to rotate in the clockwise direction. Now let's say if we have another compound wheel, and this time we're going to have a force that is directed at an angle. And let's say this force is 400 newtons. And the angle is 30 degrees above the horizontal. And let's say that there's another force of 300 newtons, and another force of 500 newtons. Now the radius of the small circle, let's say it's 1 meter again, and for the large circle, let's say it's 3 meters. So what is the net torque of the system? And let's say also that there's a frictional torque that opposes motion, and let's say it's 20 newtons times meters. So what is the net torque of the system? It's going to be easier if you calculate the net torque without friction and then add friction. Because right now we don't know if friction is acting in the counterclockwise direction or the clockwise direction. So we got to find the net torque. So if this object, or if this system, is rotating in the clockwise direction, frictional torque is going to be counterclockwise. And if the wheel is rotating counterclockwise, frictional torque will be clockwise. So let's call this force F1, F2, F3. So how can we calculate T1? We know that the torque is equal to the force times the moment arm times sine theta. But should we use this angle? It turns out that we shouldn't use that angle. The angle that we should use is the angle between the force vector and the line that's parallel to R. So the moment arm, or rather just R, is this distance of 3 meters. So if we extend that line, we need the angle between R and F. So we need this angle, which is complementary to 30. So it's 90 minus 30, which is 60. So torque 1 is going to be F times R times sine theta, or 400 times an R value of 3 times sine 60. 400 times 3 is 1200, and sine 60 is root 3 over 2. So that's 600 root 3, which is about 1039. Let's round it to the nearest whole number. It's 1039.2, but let's just say it's just 1039. Now this particular torque, is it positive or is it negative? So F1 is going to create a torque that is going to turn the wheel towards the right in the clockwise direction. So this torque is negative. Now what about F2? F2 also creates a torque in the clockwise direction, so that's going to be negative as well. So T2 is 300 times 1, so it's going to be negative 300. Now what about F3? F3 will create a force that's going to cause the wheel to rotate in the counterclockwise direction, so it's going to create a positive torque, and it's 500 times an R value of 3 meters, since it's at the edge of the outer circle, or the larger circle. So 500 times 3, that's positive 1500. Now that we have T3, let's calculate the net torque without friction initially. So the net torque is the sum of the three torques. So that's 1500 plus negative 300, which is 1200, plus negative 1039. So 1200 minus 1039, that's 161. So the net torque without friction is positive 161 newtons times meters. So the net torque with friction is going to be the difference between the two values. So if the wheel is moving in the counterclockwise direction, since the torque is positive without friction, then friction is going to oppose motion. So friction is going to be directed in the clockwise direction. So the frictional torque is not positive 20, but rather it's negative 20. So the net torque is going to be 161 minus 20. Friction is going to reduce it, and so now it's positive 141. So it's still moving in the the counterclockwise direction, but friction slows it down a bit. Now let's say if we have a simple seesaw, and let's say the fulcrum is placed at that position, and let's say if we apply a downward force of 100 newtons at a distance of 2 meters from the axis of rotation, which is at this point. And let's say this distance is 6 meters. So if we apply a downward force, what upward force will be created at this point as we exert a downward force of 100 newtons? It turns out that the torque that's applied to this side is equal to the torque that's exerted on that side. So basically the torque is simply transferred from one side to the other. The net torque is going to be the same. So the torque that you exert on this side is equal to the torque that's going to be exerted on the other side. So here's a question for you. If you apply a force on the smallest side, the output force, will it be greater or less than 100? T1 is going to equal T2. Let's call this F1 and the output force F2. It turns out that F1 times R1, where 2 is R1 and 6 is R2, is equal to F2 R2. So 100 times 2 creates a torque of 200, and that's going to be equal to F2 times 6. So F2 is going to be 200 divided by 6, which is about 33.3. So the force is reduced. So if you apply a force at the shorter side, you're going to produce a weaker force at the longer side. The stronger force is always associated with the shorter side. The smaller force is always associated with the longer side to produce the same torque. So as the force increases, or rather, as R increases, the force required to produce the same torque decreases. Since the moment arm is larger at the right side, the force that is exerted will be less. Let's try another problem like this. So let's place the fulcrum at this location. And let's say that this distance is 2 meters, and the distance here is 10 meters. And let's apply an input force of 100 newtons. So what is the output force of this simple seesaw? Is it greater or less than 100? Now the larger force is always associated with the smaller side, or the shorter side. So this time the output force is larger. So we know that F1R1 is equal to F2R2, where the input force times the input distance equals output force times output distance. F1 is 100, R1 is 10. So F2 is the output force that we're looking for, and R2, the force that corresponds to this, or the distance that corresponds to F2, is 2. So it's going to be 100 times 10, which is 1,000, divided by 2. And so the output force is half of 1,000, or 500 newtons. So notice that the output force increased by a factor of 5. So therefore, we could say that the mechanical advantage of this machine is 5, since the force increased by a factor of 5. Mechanical advantage of a machine is defined as the output force divided by the input force, which is 500 over 5. Now, mechanical advantage can also be defined as the input distance divided by the output distance, or the input lever arm over the output lever arm, which is 10 divided by 2, and that gives you 5 as well. So that's how you can calculate the mechanical advantage of a simple machine. Let's try a problem. So we have a seesaw, and we have a 30 kilogram block placed on the seesaw at a distance 3.6 meters away from the fulcrum. Now, what is the mass of another block that is placed 0.9 meters away from the fulcrum if the seesaw is to be balanced? If we wish to balance the seesaw, the torques must be equal to each other. The sum of all torques must add up to 0. Now there's two torques created. Let's call this one T1 and this torque T2. T1 plus T2 must add to 0. Therefore, negative T1 must equal T2. So they have to be the same. One is going to be positive, the other is going to be negative. So what can we do to solve this particular problem? Well, if you have a mass, we know there's going to be a weight force called mg. So this block will also exert a weight force. Let's call it m2g. So we know that T1, or negative T1, has to equal T2. And T1, which is caused by mass 1, notice that it causes the fulcrum to rotate in a counterclockwise direction. So T1 is positive. T2, the tension created by mass 2, causes the fulcrum to rotate in a clockwise direction. So T2 is negative. So T1 is going to be F1 times R1, and T2 is F2 times R2. But we know it's going to be negative. The two negative signs will cancel, so we can get rid of them if we multiply both sides by negative 1. Now F1 is the weight force mg, so let's call it m1g. R1 is 3.6. F2 is m2g times R2, which is 0.9. Now we can cancel g if we divide both sides by g. So m1r1 equals m2r2. So m1 is 30 times 3.6, that's r1, And that equals R2, which is 0.9 times M2. So the second mass is 30 times 3.6 divided by 0.9, which is 120. So the fulcrum, or the seesaw, is going to be balanced if we place a 120 kilogram object 0.9 meters away from the fulcrum. Now the next topic that we need to talk about is inertia. But before we do, let's talk about mass. When you think of mass, what do you think of? How would you define mass? As we know, mass represents the quantity of matter, but you can also think of it as a measure of inertia. Inertia is the tendency of an object to resist changes in motion. The law of inertia is associated with the first law of motion, that is Newton's first law, where an object in motion will continue in motion unless acted on by net force, and an object at rest will remain at rest unless acted on by net force. So an object with more mass has more inertia. It's easy to move a small box if you apply a force to it, but it's much more difficult to move a larger box. Let's say a 100 kilogram box versus a 10 kilogram box. It's significantly easier to move the 10 kilogram box, but it's harder to move the 100 kilogram box because it's heavier, it's more massive, and therefore it has more inertia because it has a greater resistance to any change in its motion. If we apply a force of 100 newtons, the 10 kilogram box will feel an acceleration of 10 meters per second squared, according to Newton's second law, F equals ma. The 100 kilogram box will have an acceleration of 1 meter per second squared. So because it's heavier, it has a smaller acceleration, and so it's going to move slower. The smaller box, which is lighter, will experience a larger acceleration, and so it's going to move faster. So the larger object has more inertia, and so it has a greater resistance to any change in its state of motion. So inertia and mass are related. So as mass increases, inertia increases, and it's harder to move the object. And so that's the main idea behind inertia. It's the natural tendency of an object to resist changes in its motion. Now there's another concept that you need to be familiar with, and that's rotational inertia. Rotational inertia depends on mass, but it also depends on how the mass is distributed. For example, let's say if we have a bar and we wish to rotate the bar around this axis of rotation. The inertia for this object, it turns out it's 1/3 ml squared, where L is the length of the bar. Now let's say if the axis was through the center of the bar, the inertia is significantly less. It's 1/12 ml squared, where L is the total length of the bar. As you can see, the inertia is significantly less if the axis of rotation is closer to the center of mass. If the center of mass is further away from the axis of rotation, the inertia is greater. 1/3 is larger than 1/12. Now, which one is easier to rotate? The bar on the left or the bar on the right? Let's say that the mass is the same and the length is the same. Since 1/3 is larger than 1/12, the bar on the left has more inertia. And so since it has more inertia, it's going to be harder to rotate. Now the one on the left has less inertia, so it's easier to rotate around the center of mass. Since it has less inertia, there's less resistance to any change in its motion, so if there's less resistance, it's easier to rotate. On the left side, it's going to be harder to rotate. Since there's more inertia, there's more resistance to rotation. Now let's derive a generic formula for inertia. So let's start with Newton's second law, F equals ma. Now what we're going to do is replace the acceleration with alpha times r. So let's say if we have an object that spins, we know this is the tangential acceleration, and here's the radius. The angular acceleration times the radius is equal to the tangential acceleration. So we can replace a with alpha times r. So now what we're going to do is we're going to multiply both sides by r. F times r is equal to the torque. And then it's going to be m times r squared times alpha. The quantity mr squared is equal to the inertia. So torque is inertia times alpha. Now let's compare these two equations. F equals ma and torque equals inertia times alpha. The second equation is the rotational equivalent of Newton's second law. Torque is the rotational equivalent of force. Inertia is the rotational equivalent of mass. And angular acceleration is the rotational equivalent of tangential acceleration. Now consider a problem. Let's say if we have two disks. One is small and the other is large. Now we're going to apply a force, the same force of, let's say, 100 newtons. Now the radius of the smaller disk, let's say it's 1 meter. And for the larger disk, let's say it's 2 meters. Now let's say the mass of the disk is the same. So for the first disk, let's say the mass is 5, and for the second, it's also 5. So because the size is different, the way the mass is distributed is different as well. So even though the mass is the same, the inertia of these two objects is not the same. The inertia for a disk is 1/2 mr squared. The general equation for the inertia, we said it's mr squared, but dependent on the shape, there's a constant in front of it which can change depending on how the mass is distributed and where the axis of rotation is located. In general, if the mass is further away from the axis of rotation, the inertia will increase. If the majority of the mass, if it's concentrated near the axis of rotation, the inertia will decrease. So which object will have a greater inertia value? Is it disk A or disk B? Now disk B should have a larger inertia value because the disk is larger, so the mass is further away from the axis of rotation. So let's say if the center of mass was around this circle, the center of mass here would probably be around this circle, which is closer to the axis of rotation. So because you have a larger disk for B, it's going to have more inertia. Let's calculate the inertia for each object. So it's 1/2 times the mass times the square of the radius. So 2 squared is 4, half of that is 2 times 5. For object B, it has an inertia value of 10. The units for inertia is kilograms times meters squared. Now for the other object, it's going to be 1/2 times the mass of 5 times the radius of 1 squared. Half of 5 is 2.5. So the inertia is 2.5 kilograms times square meters. So the object with a larger inertia value is going to have a greater resistance to any change in its motion. So it's going to be harder to spin disk B because it has more inertia. So therefore it has more resistance to spinning, so to speak. Now let's calculate the angular acceleration of each wheel. Let's start with the first one. So torque is equal to inertia times alpha. And torque is F times R. The force times the lever arm, which is the radius of the circle, since the force is perpendicular to it. So for the first example, F is 100, the radius is 1, the inertia is 2.5, and let's solve for alpha. So 100 divided by 2.5 will produce an angular acceleration of 40 radians per second squared. Now for the second object, the force is 100, the radius is 2, so a larger torque is exerted on the larger wheel. The inertia is 10, so what is alpha? So 100 times 2 is 200 divided by 10, that's 20. So alpha is 20 for the larger wheel. So as we can see, even though the mass of wheel A and B are the same, the inertia is not the same. So because B has a larger inertia, it experiences a smaller angular acceleration, even though the torque applied to disk B is greater. The torque is 200. It's force times the radius. So even though it has a larger torque, the angular acceleration is still significantly less. We applied a smaller torque on disk A, a torque of 100, and yet it still produced a larger acceleration. So what that tells us is that it's easy to cause disk A to rotate, but it's harder to rotate disk B. So the larger the disk, the harder it is to rotate, since it has more inertia. It has more resistance to any changes in its motion. But the smaller the disk, the easier it is to rotate. It has less inertia. Now there's some other concepts that we need to go over too. For example, work is equal to force times displacement. Now what is the rotational equivalent of force? The rotational equivalent of force is torque. And the rotational equivalent of distance or displacement is angular displacement. So work is also equal to the torque multiplied by the angular displacement. Now power is force times velocity. Power is also equal to torque times angular velocity. You can see the relationships between the two equations. So force and distance. Let's see if we can use this equation to get this equation. Now we know that distance is equal to theta times r. So if we replace distance or displacement with angular displacement times the radius, we know that F times r is equal to the torque. So work equals torque times theta. Now for the other equation, if you start with this equation, we can replace velocity with angular velocity times the radius. And F times r is the torque. So torque times angular velocity is equal to the power. Now let's say if we have another wheel. Let's apply a force of 200 newtons. So let's say if there is a rope attached to this wheel and we're pulling on the rope with a force of 200 newtons. So this force represents the tension force. And let's say we pull the rope through a distance of 40 meters. Let's say the radius of this disc, let's say it's 2 meters. How much work is done by pulling the rope with a tension force of 200 newtons a distance of 40 meters? And let's say the mass of the disk is 5 kilograms. We know that work is equal to force times displacement. So it's 200 newtons times 40 meters. 200 times 40 is 8,000. So it's going to be 8,000 joules. Now let's see if we can get the same answer using the other equation. So what can we do? How can we begin? What would you do to find the work using the equation torque times angular displacement? So let's find the torque. Torque is equal to F times R, or 200 times 2. So the torque is 400 newtons times meters. Now what is the angular displacement? We have the linear displacement, so we can calculate the angular displacement using this equation. The linear displacement is 40 meters, and the radius is 2. 40 divided by 2 is 20, so the angular displacement is 20 radians. Now that we have the angular displacement and the torque, we can calculate the work. The work required to spin the wheel for a total distance of 40 meters. So the torque was 400 and the angular displacement was 20 radians. 4 times 2 is 8, and if you add the 3 zeros you get the same answer, 8,000 joules. So you can find the rotational work by multiplying the torque and the angular displacement. Now what about the power? What is the power exerted by this force? So there's two ways in which we can calculate power. Force times velocity and torque times angular speed. Let's use both equations and let's make sure that we get the same answer. So how should we begin? We know the force and we know the torque. What we're missing is the angular velocity and the linear or the tangential velocity. So how can we calculate the angular velocity if we apply a force of 200 newtons and if we pull the rope for a distance of 40 meters? Now keep in mind, we already know the angular displacement. We said it's 20 radians. So let's save that value. What we need to do is calculate the angular acceleration. If we can find that, then we can calculate the angular speed. We know the initial speed. We're going to assume that it starts from rest, so that's 0 radians per second. We need to find or calculate the final angular speed. So we know that torque is equal to inertia times alpha, and torque is F times R. The force is 200. Well, before we do that, let's replace a few things. Inertia is 1/2 mr squared for a disk. So we can divide by R. The force is 200. The mass of the disk is 5, and the radius is 2. So 2 times 1/2 is simply 1. Therefore, 200 divided by 5 will give us the angular acceleration of 40 radians per second squared. So now that we have the angular acceleration, we can calculate the final angular speed using this equation. So the initial angular velocity or speed is 0, alpha is 40, and the angular displacement is 20 radians. 40 times 20 is 800 times 2, that's 1600. So now we need to take the square root of both sides. So the square root of 1600 is about 40. So the final angular speed is 40 radians per second. So now we can calculate the power exerted by this force. So it's equal to torque times the angular velocity. So let's calculate the instantaneous power when the angular speed is 40. Because the angular speed is not constant, it changes from 0 to 40. So we can calculate the instantaneous power and the average power. The instantaneous power is going to be the torque, which is constant. That's a constant 400. That's force times radius, F times R, times an instantaneous angular speed of 40 radians per second. So 400 times 40 is equal to a power of 16,000 watts, which is the unit of power. 1 watt represents a transfer of 1 joule per 1 second. So 16,000 watts means that in 1 second, 16,000 joules of energy is being transferred from the force to the disk. Now, if 16,000 joules of energy is being transferred every second, how much energy is being transferred in 10 seconds? Energy is equal to power multiplied by time. So that's 16,000 joules per second times 10 seconds. As you can see, seconds cancel. So 160,000 joules will be transferred in 10 seconds if the power was constant, but it's not. That's the instantaneous power. Because the speed is changing, the power is changing as well. So sometimes we need to calculate the average power. Because the speed increases at a constant rate, it turns out that the average power is simply half of this value. It's 8,000 watts. You can calculate the average power by using this equation: 1/2 times the torque times the initial angular speed plus the final angular speed. This is if the angular speed is increasing at a constant rate and if the torque is constant. Sometimes the angular speed may be constant, but the torque may be increasing at a constant rate. In this case, you need to use the average torque, which you add the initial and the final torque and then divide it by 2. So those are 2 ways to calculate the average power. But remember, the 16,000 watts is the instantaneous power. At the instant, the speed, or the angular speed, is 40 radians per second. Now let's calculate the instantaneous power using this equation. So we know the force is 200 newtons. Now what is the angular speed? I mean, not the angular speed, but the tangential speed, or the tangential velocity. We know that v is equal to w times r. So if the angular velocity is 40 radians per second times the radius of 2, then the tangential velocity is 80 meters per second. It's 40 times 2. So what's 200 times 80? 200 times 80 gives you the same answer, which is 16,000 watts. So that's the instantaneous power. Now, how long did it take for the wheel to accelerate from 0 to 40 radians per second? What is the time that it took to get there? Using this equation, you can calculate the time. The final angular speed is 40, initial is 0, alpha is 40. So if you solve for t, it took 1 second for the wheel to go from 0 to 40 radians per second. Now that we know the time it took to get there, we can calculate the energy transferred from the force to the wheel. And it's simply work is equal to force times displacement, which is, we said 200 times 40, which is 8,000 joules. A second way in which we can calculate that answer is using the average power, which we said average power was 1/2 times, in this case, the torque, which was 200 times 2, that's 400, times the angular speed, initial plus final, 0 plus 40. So that's also 200 times 40, which will give you 8,000 watts. 8,000 watts is 8,000 joules per second. And in a time of 1 second, 8,000 joules will be transferred, which is equal to the work done by the force, which is 200 times 40 meters. That's also 8,000 joules. The third way to calculate it is to calculate the rotational kinetic energy. The rotational kinetic energy of an object spinning is 1/2 times the inertia times the angular speed. It's very similar to the kinetic energy equation, which is 1/2 times the mass times the speed squared. So as you can see, mass, or inertia, is rotational equivalent of mass, and angular velocity is rotational equivalent of velocity. So let's use this equation to calculate the rotational kinetic energy. So first, we need to calculate the inertia. The inertia of a disk is 1/2 mr squared. So that's 1/2 times a mass of 5 times a radius of 2, and the angular speed is 40, the final angular speed. So 2 squared is 4, and 1/2 times a half is 1/4. These cancel. 40 squared is 1600 times 5 is 8,000. So all of the energy that was exerted by this force over a distance of 40 meters was converted to rotational kinetic energy. So hopefully you can see how these equations relate to one another. Let's try this problem. A 10 kilogram disk with a radius of 5 centimeters accelerates from rest to 30 radians per second in 6 seconds. How much work is required to accelerate the disk to this speed? So there's different ways in which we can calculate the work. One way is to use kinetic energy. Work is equal to the change in kinetic energy, in this case, the change in rotational kinetic energy. Another way in which we can calculate the work is if we could find the torque and the angular displacement, we can do it that way as well. So let's use kinetic energy. The initial kinetic energy is 0, so work is simply equal to the final kinetic energy, which is 1/2 times the inertia times the final angular speed. So let's calculate the inertia. The inertia for a disk is 1/2 mr squared. The mass of the disk is 10 kilograms, and the radius is 5. 5 squared is 25, and half of 10 is 5. 5 times 25 is 125. So the inertia is 125 kilograms times square meters. So now we can find the work. So it's 1/2 times the inertia times the angular speed, the final angular speed of 30. 30 squared is 900. Half of that is 450 times 125. So the work required to accelerate the disk to the speed is 56,250 joules. Now let's see if we can get the same answer using this equation. Now we need to calculate the torque and the angular displacement. So how can we figure out those two things? We can calculate the angular displacement by using this equation. It's 1/2 the initial angular speed plus the final multiplied by the time. The initial angular speed is 0, the final is 30, and the time is 6 seconds. Half of 30 is 15, and 15 times 6 is 90. So the angular displacement is 90 radians. Now what can we do to calculate the torque that caused this disk to accelerate. We don't have the force, but we do have the inertia. Torque is inertia times alpha. So we got to find alpha first. Let's use this equation. Omega final equals omega initial plus alpha t. The final angular speed is 30, initial is 0, and the time is 6. So 30 divided by 6 is 5. So the angular acceleration is 5 radians per second squared. So therefore, the torque, which is inertia times the alpha or angular acceleration, that's 125 times 5. And that's going to be 625 newtons times meters. So the work, which equals torque times angular displacement, is going to be 625 times 90. And you get the same answer of 56,250 joules. So now we see how much work is required to accelerate the disk. Now that we have that answer, how can we calculate the average power exerted on the disk during the 6 seconds? There's many ways in which we can do it, but we can do it this way. Power is equal to work divided by time. So 56,250 joules divided by 6 seconds is 9,375 watts. So what this number means is that every second, 9,375 joules of energy was transferred to the disk as it accelerated. That means in 6 seconds, 56,250 joules of energy was transferred to it. Now let's calculate the power using another equation. Now it's important for you to understand that the power that we have here is the average power throughout the 6 seconds. It's not the instantaneous power at a given time instant, but it's the average power. So to calculate the average power, we know power is equal to torque times the angular speed. So it's going to be 1/2 the initial plus the final angular speed, which represents the average angular speed, multiplied by the torque. Because the acceleration is constant, the disk accelerated at a constant rate, the torque is constant. But because the angular speed changes, we need to find the average angular speed. It increased from 0 to 30, so the average between 0 and 30 is 15. So it's 1/2 0 plus 30, which is 15, multiplied by the torque, which was 625. So 15 times 625 gives you an average power of 9,375 watts. So that's another way in which you can get the same answer, using the average power formula, or work over time. Now let's work on some problems associated with calculating the inertia of a system. So in this particular problem, we have 2 blocks attached to a light rod. You could say a massless rod, but everything has mass, so we're not going to worry about the mass of the rod in this particular problem. Now the mass of each block is 4 kilograms, and the rod can rotate about its center. Let's say that's the axis of rotation. And the length of the rod is about 10 meters, which means that each mass is 5 meters from the axis of rotation. How can we calculate the inertia of the system? The inertia of the system is the sum total of all of the individual inertias. So let's say that this is M1 and this is M2. So it's going to be I1 plus I2, which is m1 r squared plus m2 r squared. So it's the 4 kilogram mass times an r value of 5 meters. That's the radius, or the distance between the mass and the axis of rotation. 5 squared is 25. 25 times 4 is 100. So it's 100 plus 100. So the inertia of this system is 200 kilograms times square meters. Now, what is the inertia of the system if the axis of rotation is moved to, let's say, this 4 kilogram block? By the way, this value is the inertia when the axis of rotation is located at the center of mass. The center of mass is right between the two 4 kilogram blocks because they're the same. So the inertia when the axis of rotation passes through the center of mass is 200. But now how can we calculate it if it's at the 4 kilogram block? There's two ways in which we can do so. We can use the same process to get the answer, and we can use the parallel axis theorem. But let's use our original process. So it's going to be m1 times r1 squared plus m2 times r2 squared. So the first mass, the 4 kilogram block, is located directly at the axis of rotation, so the r value is 0. Now the second 4 kilogram block, notice that it's 10 meters away from the axis of rotation. The length of the rod is 10 meters, so this distance here is 10. So it's 4 times 10 squared. 10 times 10 is 100, times 4 is 400. So the new inertia is now 400 at this position. Now how can we use the parallel axis theorem to get the same answer? The parallel axis theorem allows you to calculate the inertia of an axis that's parallel to the axis that passes through the center of mass. So here's the equation. It's the inertia when the axis passes through the center of mass plus the total mass of the system times d squared, where d is the distance between the original axis of rotation that passes through the center of mass and the new axis of rotation, which is what we're looking for. So we could see that d is equal to the distance between the two axes of rotations, and so that's 5. So the inertia when the axis of rotation passes through the center of mass is 200. The total mass is the mass of the two blocks. 4 plus 4 is 8, and the distance between the two axes of rotation is 5. 5 squared is 25, and 25 times 8 is 200. 200 plus 200 is 400, and that's the inertia if the axis of rotation is located here. So notice that when the axis of rotation is close to the center of mass, the inertia is significantly less, which means that it's easier to rotate. When the axis of rotation is placed further away from the center of mass, the inertia is significantly larger. And if the inertia increases, that means that it's much more difficult for the system to rotate. So it's easier for the object to rotate freely if the axis of rotation is placed at the center of mass. You want the masses to be close to the axis of rotation. If the masses are further spread away from the axis of rotation, the inertia is going to be greater. And if the center of mass is located further away as well, the inertia is higher as well, which means it's harder to rotate. Now let's work on another example in which we can use the parallel axis theorem. So let's say if we have a rod of mass m and it rotates around its center, or the center of mass, and it has a length L. If you look at your physics textbook, the inertia for this system is 1 over 12 times ml squared. So that's the inertia when the axis of rotation passes through the center of mass. And the inertia for this object, let's say if it has the same mass, and let's say it also has the same length, the inertia is 1 over 3 ml squared. So use the principal axis term, or not the principal axis term, but the parallel axis term to calculate the inertia for this system. Use that equation to get this answer. So the inertia of the new system is the inertia where the axis of rotation passes through the center of mass plus md squared. So d is the distance between the original axis of rotation and the new one. So as you can see, d is half of the length of the rod. So d equals L over 2, or simply 1/2 L. The inertia at the center of mass, we said it's 1 over 12 ml squared. Now the mass is still going to be the same, so that's going to be m. The only thing that's changing is the location of the axis of rotation. So we got to plug in d. We need to replace it with 1 over 2 times L squared. So let's make some space. We don't need this side anymore. 1 over 2 L squared is 1/4 L squared. 1/2 times 1/2 is 1/4. So it's 1 over 12 ml squared plus 1/4 ml squared. So now let's get common denominators. Let's multiply 1/4 by 3 over 3. So 3 times 4 is 12. 1 over 12 plus 3 over 12 is 4 over 12. And if you divide the top and the bottom by 4, 4 divided by 4 is 1. 12 divided by 4 is 3. So this is going to be 1 over 3 ml squared, which is equal to the inertia when the axis of rotation is at the edge. Let's try this problem. Calculate the moment of inertia of a 10 kilogram rod that has a length of 4 meters with an axis of rotation located 1 meter from one of its ends perpendicular to the length of the rod. So let's say this is the rod and the axis of rotation is right here. So the length of the rod is 4 meters, which means that this side is 1 meter. It's 1 meter away from one of the ends, and the other side has to be 3 meters because the total length is 4. So what is the inertia of this system? So we need to use the parallel axis theorem equation. So the inertia of this system is equal to the inertia where the axis of rotation passes through the center of mass plus m times d squared. So let's say that the mass is uniformly distributed throughout this rod. The center of mass is located right in the middle. Now the inertia, if the axis of rotation was at the center of mass, we know it's equal to 1 over 12 times ml squared. And d, which is the distance between the new axis of rotation and the original one, which is the one that passes through the center of mass, we can see that it's 1/4 of the length of the rod. The distance between the center of mass and the end is 2 meters. So this is also 2 meters. Which means that if this is 1 meter, the distance between the two axes of rotations is 1 meter. So 1 meter out of a total distance, or the total length of 4, is 1/4. So D is 1/4 the value of L. So let's find the new equation. So it's 1/12 ml squared. That's this equation, plus the mass of the entire rod times d squared, or 1/4 L squared. 1/4 squared is 1/16. So what we have is 1/12 plus 1/16. So let's get common denominators. The common denominator between 12 and 16 is 48. So let's multiply 1/12 by 4/4 and 1/16 by 3/3. So this is going to be 4/48 plus 3/48, and of course times ml squared. So the inertia at the new axis of rotation is 4 plus 3, which is 7/48 times ml squared. So the mass of the entire rod is 10 kilograms, and the length of the entire rod is 4 meters. 4 squared is 16, and 48 is 16 times 3. So we can cancel these two numbers. So it's simply 7 times 10, which is 70 divided by 3. And 70 divided by 3 is about 23.3 kilograms times square meters. Let's try another problem. Let's say if you have 4 point masses and they're all equal. Let's say they all have a mass of 5 kilograms, and they form a rectangle. They're connected by very light rods. And let's say the distance between the two 5 kilogram objects at the top, let's say it's 6 meters instead of 4. And the distance between the two 5 kilogram objects on the left side, let's say it's 4 meters. Calculate the inertia of the system if the axis of rotation passes through the center of mass. Feel free to pause the video as you work out this example. So what we need to do is calculate the sum of each individual inertia for each mass. So it's going to be m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared. Now all of the masses are the same, and r is the distance between each mass and the axis of rotation. So r is half of 6, is 3. So each mass is located 3 meters away from the axis of rotation, and they all have the same mass. So we can add these values. This is going to be 4m times r squared, because m1, m2, m3, m4 are the same. So if you add them, you just get 4m. And then r is the same. So it's 4 times a mass of 5, so the total mass is 20. And they're each 3 meters away from the axis of rotation. 3 squared is 9. 4 times 5 is 20. 9 times 20 is 180. So that is the inertia of the system when the axis of rotation passes through the center of mass. Now what if we move the axis of rotation to this position here? Let's say if it's 2 meters away from the first 5 kilogram object. Calculate the inertia about this axis. So let's find the sum of each inertia. So mr squared, the first mass, the 5 kilogram, is about 2 meters away, so it's m times r squared, 5 times 2 squared. Now the same is true for this one. It's 2 meters away. Now for the next 5 kilogram object, it's a distance of 8 meters away from the axis of rotation. It's 6 plus 2. So it has a mass of 5, but an r value of 8. And the last one is the same. It's 8 meters away from the axis of rotation, and it has a mass of 5. So plus 5 times 8 squared. 2 squared is 4, and 4 times 5 is 20. So it's 20 plus another 20. And 8 squared is 64 times 5, that's 320. So this is also 320. 320 plus 320 is 640, plus another 40, that's 680. So that is the new inertia, or the inertia at the new axis of rotation. So now let's see if we can get the same answer using the parallel axis theorem. So the inertia at the new location is equal to the inertia when the axis of rotation passes through the center of mass plus md squared. So we have this value. It's already 180. The total mass of the system is 20. That's 5 times 4. And the distance between the new axis of rotation and the old one is 2 plus 3, which is 5 meters. So 5 squared is 25 times 20 is 500. So 180 plus 500 is equal to 680. So that is the inertia at the new axis of rotation. Now there are some other equations that you need to know. Momentum is equal to mass times velocity. That's linear momentum. Angular momentum, represented by the symbol L, is equal to the rotational equivalent of mass, which is inertia, times the rotational equivalent of velocity, which is angular velocity. So momentum is conserved whenever you have a collision and if there's no external forces acting on a system. If you have an isolated system, momentum will be conserved. Angular momentum is conserved if there's no external torques acting on the system. So in both cases, for the linear momentum and the angular momentum to be conserved, you have to have an isolated system where there's no external forces or torques acting on it. Now, force can be described as the rate of change of momentum divided by the rate of change of time. Perhaps you're familiar with the impulse momentum theorem. Force multiplied by time, which is impulse, is equal to the change in momentum, which is mass times change in velocity. It turns out that torque is the rate of change of angular momentum over time. So as you can see, these two equations are very similar. Now let's see if we can derive the second equation, or the last one that we wrote. So we know that torque is equal to inertia times alpha. And alpha, the average angular acceleration, is equal to the change in the angular velocity divided by the change in time. So we can replace alpha with delta omega divided by delta t. Now, it turns out that angular momentum is equal to inertia times angular velocity. So the change in angular momentum is equal to the inertia times the change in angular velocity. So we can replace this with delta L. So thus we could say that the torque is the rate of change of the angular momentum with respect to time. Let's try this problem. A disk of radius 0.3 meters was accelerated from rest by a constant force of 100 newtons for 20 seconds. What is the angular momentum of the disk after 24 seconds? So first we need to calculate the torque. So we have a disk and we're applying a force of 100 newtons. And the radius is 0.3 meters. So the torque is F times R, which is 100 times 0.3. So it's 30 newtons times meters. Now that we know what the torque is equal to, we can calculate the angular momentum. So we know that the torque is the change in the angular momentum divided by the change in time. So the torque multiplied by the time is equal to the final angular momentum minus the initial angular momentum. Since the disk was accelerated from rest, the initial angular momentum is 0, so we can get rid of this. So the torque of 30 multiplied by the time of 24 seconds is equal to the final angular momentum. So it's 30 times 24, and that's about 720. Now, if the angular speed was found to be 32 radians per second at this instant, what is the mass of the disk? So we know that angular momentum is the product of the inertia times the angular speed. So L is 720 and omega is 32 radians per second. So 720 divided by 32 will give us an inertia of 22.5 kilograms times square meters. Now that we have the inertia, we can calculate the mass of the disk. So let's write this value. So we know that inertia for a disk is 1/2 mr squared. So 22.5 is equal to 1/2 times the mass, and the radius is 0.3 squared. So if we multiply both sides by 2, it's going to be 45 on the left. We're no longer going to have a fraction. And then times 0.3 squared. 0.3 squared is about 0.09. So the mass is 45 divided by 0.09. So it's 500 kilograms. A turntable has an inertia of 25 and is spinning at an angular speed of 1.5 radians per second. Now if we place a block and if the inertia goes up to 32, what is the new angular speed? So this is a conservation of angular momentum problem. So the initial angular momentum must be equal to the final angular momentum. So I1 omega 1 equals I2 omega 2. So the inertia before we place the block on a turntable is 25, and the angular speed is 1.5. Now, what do you think is going to happen if the inertia increases to 32? Will the angular speed increase or will it decrease? In order for the angular momentum to remain the same, if the inertia increases, the angular speed will decrease. Let's solve for W2, or omega 2. It's 25 times 1.5 divided by 32. And so the answer is 1.17. So it decreased from 1.5 radians per second to 1.17 radians per second. A sphere rolls without slipping down an incline at a height of 20 meters. What is the translational speed of the ball as it reaches the bottom of the incline? So here's the sphere. And it has a radius r, but we don't know the mass or the radius of the sphere. Now, what about the second question? If a block was released from rest, let's say at the same height, will it have a speed greater than, less than, or equal to the sphere at the bottom of the incline? So who's going to win? Who's going to reach the incline first, the block or the sphere? So feel free to ponder about that as we solve this problem. So let's start with the sphere. So this is a conservation of energy problem. The sphere is above ground level, so it has gravitational potential energy. Now, as it rolls down, that potential energy is going to be converted into something. Where is it going? Now, the sphere has to move forward, so it has translational kinetic energy because it's moving forward. Now, the sphere is also rotating and spinning, so for any object that spins or rotates, it has rotational kinetic energy as well. So some of the gravitational potential energy goes into moving the ball down the incline, and some of it is used to cause the ball to roll or to spin as it travels down the incline. So let's begin. What is the equation for gravitational potential energy? Gravitational potential energy is equal to mgh. Kinetic energy is 1/2 mv squared, and rotational kinetic energy is 1/2 the inertia times the angular speed squared. Now, what is the inertia for a sphere? If you look into your textbook, it's 2/5 mr squared. So let's replace I, the inertia, with that result, with 2/5 mr squared. And let's not forget omega squared. So we can cancel the 2's, and if we divide both sides by m, we can cancel the mass in the equation. So what we have left over is g times h plus or equals 1/2 v squared plus 1/5 r squared times w squared. Now we know that v is equal to w times r. So w squared r squared is equal to v squared. So now what's 1/2 plus 1/5? If you're not sure, let's multiply both sides by 10. So it's 10gh, and then 1/2 times 10 is 5, and 1/5 times 10, or 10 divided by 5, is 2. 5v squared plus 2v squared is equal to 7v squared. But let's make some space. So what we now have is 10gh is equal to 7v squared. And now at this point, we have enough information in which we could simply solve for the velocity. So it's 10 times gravitational acceleration of 9.8. The height is 20. And let's solve for v. 10 times 20 is 200 times 9.8. That's 1960. And then let's divide both sides by 7. So we'll get 280. And then if we take the square root of 280, the speed of the sphere is going to be 16.73 meters per second. So let's keep that number in mind. Now, how would you calculate the speed of the block if it slides down from an incline of the same height? So let's draw a new picture. So we're going to have the same incline, but this time we're going to have a block, and the height is still 20. And the equation that we're going to use is going to be similar, but also quite different. All of the gravitational potential energy of the block will be converted to kinetic energy. Now, it doesn't have any rotational kinetic energy because the block is sliding down the incline. It doesn't rotate or spin. So mgh can only be equal to 1/2 mv squared. So let's divide both sides by m. And let's multiply both sides by 2 to get rid of the fraction. 1/2 times 2 is simply 1. So 2gh is equal to v squared. So let's plug in the information that we now have. So 2 times 9.8 times 20 is equal to v squared. 2 times 20 is 40, and 40 times 9.8 is 392. And if we take the square root of 392, that will give us an answer of 19.8 meters per second. So this is the speed of the block as it slides down. Notice that it's significantly higher than the sphere. The speed of the sphere was about 16.73 meters per second. And it makes sense why the block slides down a greater speed, or with a greater speed. All of the potential energy went into translational kinetic energy because the box, it doesn't rotate. So all of that potential energy went into its forward motion, whereas the sphere had to use some of its gravitational potential energy to spin or to rotate, and therefore there was less gravitational potential energy available to convert into its forward motion, and that's why the sphere moved with a smaller forward speed. Now the box, all of its gravitational potential energy went into its translational kinetic energy, and that's why the box wins all the time. That's why it's going to slide down the incline with a greater speed, because all of the potential energy went into its forward motion, whereas the sphere, only most of the energy went into its forward motion. Some of it was used to spin or cause the sphere to rotate. Now, let's say if we have a pulley that is made up of a disc and it has a rope attached to it. Now, let's say there's a block. And the mass of the pulley is 4 kilograms. And it has a radius of 2 meters. The mass of the block, let's say it's 5 kilograms. Calculate the net acceleration of the system. And let's say this is ground level, and it's at a height of 10 meters. How can we find the downward acceleration of the system? Feel free to pause the video as you work out this example. One way that you can find the acceleration is by taking the net force, dividing it by the total mass, including the inertial mass of the pulley. Now the only force that accelerates the system downward is the weight force of the block. It's going to cause the whole system to move this way. Now there's no frictional forces that opposes motion. So the only force that we have to worry about is the weight force divided by the total mass. So we have the mass of the block and the inertial mass of the pulley. Now, the inertial mass is not simply just the 4 kilograms. The inertial mass of the pulley, it's really inertia divided by r squared. The general equation for inertia is it's mr squared times some constant c. So I over r squared, it's really equal to the constant times the mass. And so this inertial mass is the constant c times m. For example, the inertia of a disk is 1/2 mr squared. So in this case, c is a half. So what I would do is represent the inertial mass as being I over r squared. And then simply plug in whatever the inertia is for that object. In this case, the inertia of the disk is 1/2 m times r squared. And then divided by r squared. So these two cancel, and it's simply 1/2 m. So that's the inertial mass that we need. So the acceleration is simply mg divided by the mass of the block plus 1/2 the mass of the pulley. If you do it this way, it's going to work out. And that's the fastest way to calculate the acceleration. So the weight force is simply 5 times 9.8. The mass of the block is 5 plus 1/2 the mass of the pulley, which is 4. 5 times 9.8 is about 49. Half of 4 is 2 plus 5 is 7. 49 divided by 7 is 7 meters per second squared. So this is the acceleration of the system. Now granted, the acceleration is negative because it's in a downward direction, but we're not going to focus on direction in this problem. We just want the magnitude of the acceleration. Now we're going to calculate this acceleration two ways. By drawing a free body diagram and using the tension force to help us calculate it, and also using conservation of energy to get the acceleration. So we're going to confirm that this answer is indeed correct using two other techniques. So let's start with the block. The block has a downward weight force and it has an upward tension force that slows the descent of the block. And so the net force of the block is directed in a downward direction. The net force of the block is the difference between the weight force and the tension force. Now the weight force is greater than the tension force, and so that's why I wrote it as W minus T, so I can get a positive value for the net force. Now the net force of the block is the mass of the block times the acceleration, according to Newton's second law, F equals ma. The weight force of the block is the mass times the gravitational acceleration, minus T. So if we solve for T, if we move negative T from the right side to the left side, it's going to be positive T. And if we move positive ma from the left side to the right side, it's going to be negative ma. So the tension force is the difference between the weight force and the acceleration. So if you need to calculate the tension force in a problem, this is it. This is the equation you need to use. Now let's focus on the pulley system. The pulley is going to have an equal tension force, but that's in the opposite direction. The rope pulls on the pulley and causes it to rotate in the counterclockwise direction. Now the torque is equal to inertia times the angular acceleration. And the torque is force times the radius, or the tension force. I'm going to write TF for tension force to distinguish it from tau, times the radius, that is equal to the inertia, which is 1/2 mr squared, times alpha. So this is TF, tension force. So we could divide both sides by the radius. So therefore the tension force is equal to 1/2 the mass of the pulley times the radius times alpha. Now we know that tangential acceleration is equal to the angular acceleration times the radius. So if we divide both sides by r, the tangential acceleration divided by the radius is equal to the angular acceleration. So let's replace alpha with a over r. So then the radius cancel, and so we have that the tension force is equal to 1/2 the mass times the acceleration. So as you can see, the inertial mass, or the equivalent inertial mass, is 1/2 m, which is what we used in the last example. So now what we're going to do is we're going to replace the tension force with the equation that we have here. So let's replace TF with mg minus ma, and that's equal to 1/2 ma. So now let's add ma to both sides. So mg is equal to ma plus 1/2 ma. And let's take out the GCF, which is a. So if we factor it out, it's going to be a times m plus 1/2 m. Dividing both sides by that term, we can see that the acceleration is going to be mg divided by m plus 1/2 m. So now let's calculate the acceleration. Lowercase m is 5, g is 9.8, divided by 5 plus 1/2 times the mass. That is the mass of the pulley. 5 times 9.8 is 49. Half of 4 is 2 plus 5 is 7. So the acceleration is still 7 meters per second squared. So we get the same answer as we could see here. So now let's calculate the acceleration using conservation of energy. Now, what forms of energy do we have initially? The pulley doesn't have any rotational kinetic energy. It's not spinning, and it's not going to fall down. It's fixed in place. So because it doesn't have the potential to fall, it doesn't have gravitational potential energy. The block has potential to fall, and so it has stored gravitational potential energy. So that's the only form of energy that we have initially. Now, as the block begins to accelerate towards the ground, some of the potential energy is going to be converted to kinetic energy, because the block will begin to move in a downward direction. So the block will have kinetic energy just before it hits the ground, after it falls a distance of 10 meters. As it falls, the pulley will begin to spin, and as it rotates, it's going to have rotational kinetic energy. Gravitational potential energy is equal to mgh. The kinetic energy of the block is 1/2 mv squared. And the rotational kinetic energy of the pulley is 1/2 times the inertia times the angular speed squared. Inertia is 1/2 mr squared. So let's replace I with 1/2 times the mass of the pulley times the radius squared. Now let's keep in mind that the tangential velocity of the pulley is equal to the angular velocity times the radius. So therefore, v squared is equal to w squared, or omega squared, times r squared. So let's replace r squared omega squared with v squared. So what we now have, let's move this somewhere else. mgh is equal to 1/2 mv squared plus 1/4 m, and then r squared omega squared is simply v squared. So at this point, we can plug in everything that we have, and let's solve for v. The mass of the block is 5, gravitational acceleration is 9.8, and the block is at a height of 10. We're looking for v, and the mass of the pulley is 4. So we know that 5 times 9.8 is 49, times 10, that's 490. Half of 5 is 2.5, and 1/4 times 4 is simply 1. So 1 v squared plus 2.5 v squared is 3.5 v squared. Now let's divide both sides by 3.5. So 490 divided by 3.5 is 140, and that's equal to v squared. So let's take the square root of both sides. And so the tangential velocity is about 11.832 meters per second. Now keep in mind, this is the tangential velocity of the pulley, and this is also the final speed of the block just before it hits the ground, because they have to move at the same rate since they're connected by the rope. So now that we have the final speed, how can we use that to calculate the acceleration of the block? So if we focus on the block, it's going to have a vertical displacement of 10. And we have the final speed, which is 11.832. And we have the initial speed. It accelerated from rest, so it's 0. Now, to find the acceleration, we can use this equation. So the final vertical speed is 11.832 squared. Initial speed is 0. We're looking for a. The vertical displacement is 10. So it's 11.832 squared, which is 139.996, which I'm going to round it to 140. And 2 times 10 is 20. So if you divide both sides by 20, 140 divided by 20 gives you an acceleration of 7. So this is another way in which you can get the same answer, using conservation of energy. Let's try this problem. So we have a 10 kilogram block attached to a 30 kilogram pulley through a rope. So here's the pulley, and here's the block. The radius of the pulley is 5 meters. And the mass of the pulley is 30 kilograms. The mass of the block is 10 kilograms. Now this time we have friction provided by the pulley. What is the acceleration of the block? So let's do it the easy way, the first method that we used in the last example. So the only force that accelerates the system in a downward direction, in the direction of motion, is the weight force. Now we need to subtract this force by any forces that opposes the direction of motion, which is the frictional force. Now we're going to divide that net force by the total mass. That is the mass of the block and the inertial mass of the pulley. The best way to find the inertial mass is using this expression, I over r squared. So this equation should give us the answer. The weight force is simply mg. Now, we have the frictional torque. Torque is force times the radius. So the frictional force is the torque divided by the radius. So it's T over R, or tau over R. And the inertia of the disk is 1/2 mr squared, which will be just 1/2 m. So now let's calculate the acceleration. So it's the weight force, mg, which is 10 times 9.8 minus the frictional torque of 80 newtons times meters divided by the radius of the pulley, which is 5. So the frictional force is 80 over 5 divided by the mass of the block, which is 10, plus 1/2 times the mass of the pulley, which is 30. So 10 times 9.8 is 98, and 80 divided by 5 is 16. Half of 30 is 15 plus 10, that's 25. 98 minus 16 is 82, and 82 divided by 25 is about 3.28. So this is the acceleration of the system, 3.28 meters per second squared, which is also the acceleration of the block. Let's try another problem. Let's say if we have a block on a horizontal frictionless surface and it's attached to a pulley which is attached to another hanging block. Now the mass of the first block is 10 kilograms. Let's call this M2, and the mass of the second block is going to be 5 kilograms, and we'll call it M1. And the mass of the pulley is 8 kilograms. And it's going to have a radius, let's say the R value is 2 meters. What is the acceleration of the system? Let's solve it using all three techniques. So first, let's do it the easy way. The acceleration of the system is going to be the net force, which is all of the forces that's going to accelerate it in the direction of motion, and there's only one. The weight of this object causes everything to move towards the right. So that's going to be the weight force. There's no frictional force, so we don't have to worry about that in this problem. Divided by the total mass. That's M1 plus M2 plus the inertial mass, which is inertia over r squared. So the weight force is M1g. And the inertia of a disk is the same as before. It's 1/2 mr squared divided by r squared. So these two cancel, and simply 1/2 the mass of the disk. So the acceleration is going to be 5 times 9.8 divided by M1, which is 5, plus M2, which is 10, and 1/2 the mass of the pulley. So 1/2 of 8 is 4. 5 times 9.8 is 49. 5 plus 10 plus 4 is 19. And 49 divided by 19 is equal to 2.579 meters per second squared. So that's the acceleration of the system. So now let's use the second method. Now let's use the second method. Let's use tension to calculate the acceleration. So there is an upward tension force, which we'll call T1, that slows the descent of the 5 kilogram block. Otherwise, without that tension force, the 5 kilogram block will descend at a rate of 9.8 meters per second squared. So it's decelerating at 2.6 or 2.579. So T1 is the tension force that slows it down. Now, that must means that there's another tension force that's equal and opposite to T1. It's going to be T1, but it's in the opposite direction. So that is the tension force that accelerates the pulley in the clockwise direction. Now there's another force, T2, that pulls block 2 towards the right, which means that there must be an equal and opposite tension force. Let's move this out of the way. There must be another T2 force that's in the opposite direction of the other T2 force that causes the pulley to slow down from turning to the right, so to speak. T2 causes the pulley to rotate towards the left or in the counterclockwise direction. But because the entire system is moving towards the right, that means that the net torque on the pulley has to be in a clockwise direction, which means that T1 has to be greater than T2 because the whole system is moving this way. So the torque, the net torque acting on the pulley is equal to the net force on the pulley multiplied by the radius. The net force is the difference between the two tension forces acting on the pulley. So it's T1 minus T2 times the radius of the pulley, or the disc. And let's just make a note that the mass of the pulley is still 8 kilograms, since I deleted it to make space for T2. So now let's go back to this equation. The torque is equal to the inertia of the disc times the angular acceleration. So that's equal to T1 minus T2 times R. Inertia is 1/2 mr squared times alpha. So if we divide both sides by r, we could cancel one of the r's on the left side. So what we have is 1/2 m times r times alpha, and that's equal to T1 minus T2. Now, the tangential acceleration is alpha times r. So we can replace r times alpha with acceleration. So now let's save this equation. Let's come back to it later. We need to write the equations for the other tension forces. So let's just leave this over here for now. Now let's focus on this system. There's a downward force, which is the weight force, m1g, and there's also a downward net force. The net force is the difference between the weight force, m1g, and the tension force. Now, I'm not too concerned about the direction of the net force. All I want to calculate is the magnitude of the net force. Now I know that the weight force, m1g, is larger than the tension force T1 because the whole system is going to accelerate in that direction. So I want a positive value for the net force. So I took the larger weight force and subtracted by the smaller tension force T1 to get a positive net force. Now the net force is always equal to ma based on Newton's second law. So let's solve for T1. So T1 is negative on the right side, which means that it's going to be positive on the left side. M1A is positive on the left side, which means that it's going to be negative on the right side. So this is the equation for t1. That's how you can calculate it if you know the acceleration. But we're going to use it later. We're going to plug it into this formula once we get the formula for t2. Now, for block 2, there's only one force acting in the horizontal direction, and that's the tension force T2. So therefore, T2 is the net force, since that's the only force acting on block 2. So T2 equals net force, and the net force on block 2 is simply the mass of block 2 times the acceleration, according to Newton's second law. So now let's plug in everything into this equation. So we know that 1/2 ma is equal to T1, which is m1g minus m1a, and then minus T2, or minus m2a. So what we're going to do is we're going to take these two values and add it to both sides. So we're going to move it from the right side to the left side. So it's negative on the right side, and it's going to be positive on the left side. So 1/2 ma plus m1a plus m2a is equal to m1g. So now let's factor out the common term, the GCF, which is a. So a times 1/2 of m plus m1 plus m2 is equal to m1g. So if we divide both sides by this term, we can see that the acceleration of the whole system is m1g divided by 1/2 m plus m1 plus m2. So let's calculate the acceleration. m1 is the 5 kilogram block. The mass of the pulley is 8 kilograms, and m2 is 10. So 5 times 9.8, we know it to be 49. Half of 8 is 4, plus 5, that's 9, plus 10 is 19. And 49 over 19 is equal to 2.579, which is the acceleration that we calculated earlier. So as you can see, this is another technique that you can use to get the same answer. The first method is easier, but for some of you out there, you may have to do it this way if you have an exam where you have to show your work. So now let's use conservation of energy to get the same answer. So choose a height for the block. It doesn't matter what height you choose. The answer is going to be the same. So let's say that the height of the block is 20 meters above ground level. Calculate the final speed of the block just before it hits the ground, and then use that information to calculate the acceleration of the system. So only block 1 has energy. It has the potential to fall. Everything else can't fall right now. The pulley is fixed in place, and block 2 can only slide horizontally, provided, of course, if block 1 hits the ground before block 2 falls off the edge. So the gravitational potential energy of block 1 is going to be equal to the kinetic energy of block 1, because as it falls down, it's going to be moving. Any object that moves has kinetic energy. Block 2 is going to have kinetic energy because it's moving forward, and the pulley will have rotational kinetic energy as it begins to spin. So all of the potential energy stored in block 1 is going to be converted into these different forms of kinetic energy. So the gravitational potential energy of block 1 is simply m1 times g times h. And the kinetic energy of block 1 is 1/2 m1 v squared. Now we don't have to write v1 squared because the velocity or the speed of every object is going to be the same because they're attached to the same rope. And then this is going to be plus 1/2 m2v squared. That's the kinetic energy for block 2. And then the rotational kinetic energy of the pulley is 1/2 inertia times the angular speed squared. So now let's plug in the information that we have. So M1GH, M1 is 5, G is 9.8, and the height is 20. And this is equal to 1/2 M1, which is 5, times V squared, plus 1/2 M2, which is 10, times V squared, plus 1/2. The inertia of the disk is 1/2 mr squared times omega squared. Now keep in mind that the speed is equal to the angular speed times the radius. So V squared is omega squared times r squared. Five times 20 is 100, and 100 times 9.8 is equal to 980. Half of 5 is 2.5, and half of 10 is 5. 1/2 times 1/2 is 1/4, and the mass of the pulley is 8. And r squared, omega squared, we're going to replace it with v squared. So 2.5 plus 5 is equal to 7.5 v squared. 8 divided by 4 is 2. And 2 plus 7.5 is 9.5. So now let's divide both sides by 9.5. So 980 over 9.5 is about 103.158. So that's equal to v squared. So we need to take the square root of both sides. So therefore, the final velocity, or the final speed, just before the 5 kilogram block hits the ground is about 10.157 meters per second. And now that we have the final speed, let's use this equation to calculate the acceleration. So the final speed is 10.157 squared. The initial speed of the 5 kilogram block is 0. We're looking for A, and the vertical distance that it travels is 20. Now, if you plug in -20 for the vertical displacement, because the 5 kilogram block is moving in a negative y direction, then the acceleration is going to be negative because it's accelerating in a negative y direction. But the two negative signs will cancel, which means the right side is going to be positive overall. But either case, you can always add the negative sign to the acceleration because you know the direction already. 10.157 squared is 103.158. And 2 times 20 is 40. So 103.158 divided by 40 gives you an acceleration of 2.578 meters per second squared. So we get the same answer. Okay, let's try this problem. So we have a 10 kilogram block on a horizontal surface. Let's call it M2. And it's attached to a pulley, which is attached to a hanging mass of 6 kilograms, which we'll call M1. Now the radius of the pulley is 4 meters, and the mass of the pulley is 12 kilograms. And we have friction on this horizontal surface, and the coefficient of kinetic friction, mu k, is 0.20. So how can we calculate the acceleration of the 6 kilogram block, or for this entire system? So the acceleration is going to equal the net force, meaning all of the forces that accelerate this object in a direction of motion, which is only the weight force of the 6 kilogram block, that's m1g, minus any forces that oppose that motion, which is the frictional force that's acting on block 2, so minus F, divided by the total mass of the system. That's m1 plus m2 plus the inertial mass of the disk, which is inertia over r squared. And if you replace inertia with 1/2 m r squared, the r squared will cancel and it's simply 1/2 m. So the acceleration is going to be m1g, which is 6 times 9.8, and the frictional force is mu k times the normal force, where the normal force is simply the weight force acting on m2. So it's going to be m2g. So this is minus mu k, which is 0.20, times, okay, I'm running out of space, so I'm going to do it over here. So mu k is 0.20, m2 is 10, the g is 9.8. So 0.2 times 10 is 2, and 2 times 9.8 is 19.6. So that's the frictional force acting on block 2. It's 19.6 newtons, divided by the total mass. m1 is 6, m2 is 10, and 1/2 the mass of the pulley, half of 12 is 6. 6 times 9.8 is 58.8 minus 19.6, and that gives us a force of 39.2. 6 plus 10 plus 6 is 22. So the overall acceleration of the system is 39.2 divided by 22, and that's 1.781 meters per second squared. Now let's say if we have a pulley made up of a disc that is attached to 2 blocks. Let's say the first block has a mass of 10 kilograms and the second block has a mass of 6. Let's call this M1 and M2. And let's say the mass of the pulley is 8 kilograms and it has a radius of 2 meters. What is the acceleration of the system? So because block 1 is heavier than block 2, we know that the system is going to move this way. To find the acceleration, it's going to be the force that accelerates the system in a direction of motion, that's the weight force, which is m1g. And the force that opposes motion is the weight force of block 2, and that's m2g, divided by the total mass, which is the mass of block 1 plus the mass of block 2 plus the inertia over r squared, which for a disk it works out to be 1/2 m. So this is going to be the acceleration of the system. So m1g, that's 10 times 9.8 minus m2g, or 6 times 9.8, divided by the total mass. m1 is 10, m2 is 6, plus half of the mass of the pulley, which is 4. So 10 minus 6 is 4, and 4 times 9.8 is 39.2. 39.2 is the same as 10 times 9.8 minus 6 times 9.8. You can subtract these two because they're multiplied to a common number of 9.8. 10 plus 6 plus 4 is 20. So 39.2 divided by 20 is equal to an acceleration of 1.96 meters per second squared. So that's the acceleration of the whole system. Now let's see if we can get this equation using tension force. Block 1 has a weight force m1g, and it has an upward tension force T1, which means there's a downward tension force on a pulley, that's T1. Block 2 has a weight force m2g and an upward tension force T2, which means there's a downward tension force on the pulley T2. Now we know the whole system's moving to the right, so that means that T1 is greater than T2. So the torque on the pulley is equal to the difference in tension force, T1 minus T2, multiplied by the radius of the pulley. Now the tension force is inertia times alpha. And the inertia of a disk is 1/2 mr squared. So just like before, we're going to divide both sides by r. So what we have left over is 1/2 mr times alpha, and that's equal to T1 minus T2. And we know that acceleration is alpha times r. It's angular acceleration times the radius of the circle. So let's replace r times alpha with a. So 1/2 ma is equal to T1 minus T2. So now, let's write an equation for T1 and T2. So we have a net downward force acting on block 1. That net force is equal to the difference in the weight force and the tension force. Since this system is moving this way, m1g is greater than T1. So m1g minus T1 is equal to the net force. Now the net force is equal to m1a. That's the net force in block 1 according to Newton's second law. So if we solve for T1, we need to move T1 from the right side to the left side, so it's going to change from negative to positive. And we're going to move positive m1a from the left to the right, so it's going to be negative on the right side. So this is the expression for T1. Now let's do the same thing for T2. The net force on block 2 is an upward force. So that means that tension 2 is greater than the weight force if block 2 is going up. So it's going to be T2 minus m2g instead of m2g minus T2. Now the net force on block 2 is m2a instead of m1a. So to get T2 by itself, we need to move m2g from the right side to the left side. So it's going to change from negative to positive. So m2a plus m2g is equal to T2. So that's the expression for the tension force. By the way, if you get a problem like this, and if you need to find T1 or T2, once you have the acceleration, plug it into one of these formulas. And that's how you can find the tension force T1 and T2. So now let's go back to this equation. So at this point, we no longer need this picture. So let's get rid of it. And let's get rid of this. And this as well. So 1/2 ma is equal to T1, which is m1g minus m1a, and then minus T2, which is this value, m2a plus m2g. So now let's distribute the negative sign. So 1/2 ma is equal to m1g minus m1a minus m2a minus m2g. So we need to get a by itself. So everything that has an a, let's move it to the left side. So these two terms, they have an a value, and they're negative on the right side. So if we move it to the left, it's going to be positive. So 1/2 ma plus m1a plus m2a is equal to m1g minus m2g. So now at this point, we can factor out the GCF, the greatest common factor, which is a. So then it's 1/2 m plus m1 plus m2, and that's equal to m1g minus m2g. Now let's divide both sides of the equation by this term. So this will give us the final answer. So the acceleration is m1g minus m2g divided by m1 plus m2 plus 1/2 ma, which is the same equation that we had before once we calculated the acceleration, and that gave us a value of 1.96 meters per second squared. So this is going to be the last problem of the day. Let's say if we have an incline and there's a pulley, and on the incline is a block attached to the pulley, and there's another block. Let's call this M1, M2. M1 is going to be 10 kilograms, M2 is going to be 15 kilograms, and the mass of the pulley, let's say it's 20 kilograms. And the radius of the pulley, let's say it's 4 meters. And let's say that there's friction on the incline, where mu k is equal to 0.15. That's the coefficient of kinetic friction. And let's say that the angle of the incline is 30 degrees. So what is the acceleration of the system? And first, what direction will it accelerate? Will it go towards the right, or will it travel towards the left? So we need to find which force is greater, the weight force of block 1 or the force of gravity, the component that accelerates it in this direction. So the weight force is m1g, which is 10 times 9.8, and so that's 98 newtons. Now the component force of gravity that accelerates block 2 this way, let's call it Fg. Fg is mg sine theta. Now, if you're wondering why that's the case, let's say if you have an incline and you have a block. This block has a downward weight force called mg, or in our case, m2g. If we draw a triangle where this is the hypotenuse, we can see that the normal force of the block is equal to this side. And the component of gravity, it's parallel to this component of the triangle. So this angle is theta, which means this is theta. So let's say if this is 30, this is the right angle, this is 60, which means that this must be 30 as well, if you draw it correctly. So that's theta. This part of the triangle is mg cosine theta. It's the adjacent side. Cosine theta is the adjacent side divided by the hypotenuse. So if you rearrange the equation, you're going to get m2g cosine theta. Now, opposite to the angle is this side, which is m2g sine theta. Sine theta is the opposite side divided by the hypotenuse. if you rearrange it, you'll get m2g sine theta. So let me explain. Let's call this side x, and let's say this side is y. So cosine theta is equal to the adjacent side x divided by the hypotenuse, m2g. So if we solve for x, we need to cross multiply. So m2g cosine theta is equal to x. And x is the same as the normal force, so m2g cosine theta is equal to the normal force. Now, let's do the same thing for y. According to SOHCAHTOA, sine theta is equal to the opposite side, which is y, divided by the hypotenuse, which is the side across the box, or the 90-degree angle. And that's m2g. So if we cross multiply, y is equal to m2g sine theta. And notice that y is parallel to Fg, the component of the force of gravity that accelerates the block downward. So Fg is m2g sine theta. So now you know where those equations come from. So let's find Fg. Let's see what the value is. So m2 is 15, g is 9.8, times sine 30. Sine 30 is 1/2. And 15 times 9.8, that's 147 times 0.5. So Fg is equal to 73.5 newtons. So let me write these values here. So because the weight force is greater, this system is going to turn in this direction. And friction is going to oppose motion. So that means if the system is going this way, friction is directed the other way. So now we could find the acceleration now that we know what direction the system is going to travel towards. So the acceleration is going to be the forces that accelerate it in a direction of motion, which is the weight force, minus the forces that opposes motion, which is Fg. It opposes the motion of the weight force, and also the frictional force opposes it. So it's the weight force minus Fg minus the frictional force divided by the total mass, which is m1 plus m2 plus 1/2 the mass of the pulley. So let's calculate the frictional force before we plug in everything into that equation. So the frictional force is equal to mu k times the normal force. And we know that the normal force is mg cosine theta. So this is going to be 0.15 times mass 2, which is 15, times gravitational acceleration, 9.8, times cosine 30. 0.15 times 15 times 9.8 times cosine 30 is about 19.096 newtons, or 19.1. So the acceleration is the weight force of 98 minus Fg, 73.5, minus 19.096, divided by m1, which is 10, plus m2, which is 15, plus half of the mass of the pulley, which is 20. So 98 minus 73.5, that's 24.5, minus 19.096. So the net force in the direction of the system, or in the direction of motion I should say, is 5.404 newtons, and the total mass is 10 plus 15 plus another 10, which is 35 kilograms. So force over mass will give you the acceleration, and that's going to be 0.1544 meters per second squared. So that is it for this video. Thanks for watching. and I hope you found it to be educational. Have a great day.